So I decided to extend my course based on a question that was asked the other day. So a student asked me when we were discussing the expansion of the universe if the universe, if the universe could expand if it has curvature, or he was asking me if this implies that the universe has curvature. I wasn't too clear because all I was trying to do with the Big Bang example was to show you how you could just multiply things, and then eventually we'll see that some multiplications lead to curvature, as we'll see here. But so in that case, I was only considering the flat case, where universe is just as a whole flat. Yeah, sure, we had some curvature due to the Earth and some black holes, but then we'll see these are too small. So as a whole, the universe is flat, but as a whole, the universe could also be curved, either positively curved or negatively curved. So let's see what this means. Okay, the shape of our universe. So if you recall, this is what we wrote down to have an expanding flat universe, where this is the expansion parameter. I think we just took a general case where it was t, so as time goes on, this gets bigger and bigger and bigger, and the universe is accelerating. The universe is expanding and is also accelerating. This is just marking the expansion of the universe. We'll see what we can normally write. So, like I just said, our universe could be approximately flat, and in fact, we could describe our universe as just a box of gas. So normally, if we have a box of gas, we have some oxygen atoms, some hydrogen, any type of atoms, and just bang up against each other and they bounce off against the walls. Well, since there's about 2 trillion galaxies in our universe, we could just say, okay, each of these points, instead of them being atoms, they're just whole galaxies. And what our observation shows us is that each of these galaxies are so I'm in this galaxy and I'm looking at all the other galaxies around me, and they're all moving away from me. So I'm not moving towards one galaxy or another galaxy, they're all moving away. And this is why we say the universe as a whole expanding, so it's like the box is expanding. And yeah, we consider the flat case, and in one of these galaxies, such as our Milky Way, there could be 10 to 100 billion solar systems. Solar systems. So this should be pretty convincing why the curvature of the Earth doesn't matter, because one of these dots out of 2 trillion, there's 2 trillion of these dots in the universe, about 2 trillion, and then this is just, within these dots, our Earth is just, our solar system is just 1 out of billion. So this should be, it should be reasonable to consider this as to just neglect everything that happens inside the Milky Way, each of these universes. So yeah, so we showed that the universe is flat. It's just like a flat box. It kind of just expands. But what does it mean for the universe to have curvature? Well, we'll talk about a net positive curvature. And we say the universe is closed because if it has a net positive curvature, it kind of it circles back onto itself. So this is a sphere, except we picture like normally a sphere, a two-dimensional surface and three-dimensional. In 3 dimensions, the surface of the ball is only 2-dimensional, but here the surface is 3-dimensional. So, and it's expanding, it's getting bigger. So what this means is it's closed. Well, we can't really walk around the whole universe because it's expanding too fast, but let's just say, strictly speaking, that the universe is not expanding. Then what closed means is we could walk around, we could go in a straight line in the universe, and then eventually come back to ourselves. So it's spherical, okay, closed universes, not open. So what causes the universe to either be flat or have positive curvature, and we'll later see negative curvature? Well, it depends on how fast the universe is expanding compared to how much matter is in the universe. So closed universes, So there is a critical density, which we could say, okay, this is the density of matter that if our matter in the universe is greater than this, the curvature is positive. If it equals this, then it's flat, and if it's less than this, it is negatively curved. So in this case, our matter density, or in well, we don't really know if our universe is closed, flat, or has positive curvature, no curvature, or negative curvature. But the density, if it had positive curvature, the density of the mass would be greater than this density, which we'll get to. This is called a critical density. So, and this also expands for the same reason as the flat universe. So it gets bigger. The flat universe expansion is caused by dark energy, or in other words, the popping in and out of existence of particles. Particles can pop in and out of existence. They create particles, antiparticle pairs, and then they go away, and this fuels the expansion of the universe. It's also called the cosmological constant. So what we see is we see something special for universes with positive curvature. So they grow, they grow, they grow, and then they hit a maximum point. And since the matter density is larger than this special value, then gravity starts taking over again, and it starts shrinking, and then it might go to a point again. That's called a big crunch. There is also something else it could do called the big bounce, where it doesn't really. I'm not too sure about this. I'm not familiar with the big bounce, but it reaches kind of not a point, but like a very special radius where it starts expanding again. So it expands, shrinks, and then expands. Um, I think this is what loop quantum gravity predicts, since we're talking about quantum gravity models. String theory actually predicts 11 dimensions for our universe. Loop quantum gravity only predicts 4. We don't see the extra dimensions because they're small and curled up, but that's for another time. That's just a side note. Okay, so this was a sphere. We said this positive curvature creates a sphere, and then this negative curvature creates a hyperbola, so as shown in these figures, these graphs. And we say this is open, and another feature. Sorry, so in the positively curved universe, the triangles are all greater than 180 degrees, and then with negative curvature, all the triangles must be less than 180 degrees. So that's another side. So we call this hyperbolic geometry. And then there is a famous artist called Escher, and he really likes doing these hyperbolic spaces. So here is a two-dimensional representation of a hyperbolic space. So how could you relate what we see here, this open universe, this expands forever, into these 2D figures? So what you can do is you could just look at a certain section of this hyperbolic geometry, and then I think I did like a little trial run. So so pretty much you could just take a line, a hyperbolic line here, and then you can map it down to a disk, and this is called a Poincare disk. You should look it up. But anyway, if you take something smaller, this would be here, which you could see it from here, these little guys, and then take another one, it'll be even smaller, and then if you take a big one like this, then it'll just wrap around, so you could just project this down to a plane. And then it gets very interesting. You could play with this. The open universe is like a flat universe in the sense that it'll just keep on expanding. And like I said, it's negatively curved instead of flat because the matter density of the universe is less than a certain critical density, and this critical density is given by some factors, 3 pi. This is Newton's gravitational constant, and this is called the Hubble's constant, which describes the expansion of our universe. So what is the Hubble's constant? Well, it's just it's like how fast the galaxies. So if you have 2 points, they don't even need to be galaxies. But I'm just going to say galaxies just because this is a scale which we measure the Hubble constant. So how fast the galaxies are moving away from each other, so the speed of the velocities, the speed of the galaxies, versus how far the galaxies are apart, or over how far the galaxies are apart. So we just call that A. I think we used A for distance when we were talking when we wrote down the distance equation, like A t dx delta x delta y delta z. So what do we measure? What do we look out into the universe and we see that the galaxies are we see the value of the Hubble constant is this, and what this means is that for every about a lot of miles, so every huge distance, the galaxies will be moving away from each other at this speed. So I kind of gave a little illustration of this. So these are 2 galaxies separated by a large amount, many miles apart, and then what we see is that they move away from each other at 45 miles per hour. But in this depiction, it's just they move away from each other half the speed. So then galaxy 1, we'll see galaxy 2 moving away at 45 miles per second, and galaxy, likewise, they'll see each other. So this is really interesting. So this has to do with this critical density. So if, like I said, if the matter density is greater than this, the universe is positively curved. If it's less than this, it's negatively curved. And if it equals this, it's flat. So, but what we see is that the universe is expanding. Okay, so this is not only expanding, but it's accelerating. So this value goes up. But this Hubble constant goes down because what happens is that this value, so the distance, the total separation, is actually going up more than the rate of change, the change in velocity. So yeah, sure, this 45 miles per second is getting greater and greater and greater as we speak. But then also the distance scale, which we're considering this, is also getting greater at a faster rate than this. So these 2 galaxies would separate from each other. The distance between them will be much greater than so the change in the distance between them will be much greater than the change in their speed. And that's pretty much what I described. So good news, kind of, I guess. I don't know if it's good or bad, but the density of our universe, this is the total matter density, we'll represent with this. It also decreases too. So it decreases such a way that for closed universes, which, like I said, if it's closed, positive curvature, if the matter density of our universe is greater than this critical value, this critical density up here, which is why that it expands to a certain point and it starts contracting again because of gravity. So I'm going to say this is P naught, so this is greater than 1, and then this is equal 1. The universe is flat, and then obviously if it's less than 1, then it'll be negatively curved, and then, like I said, these 2 cases, they expand forever. So what's nice is that the matter density also decreases in such a way that if at one point in time the universe was closed, it will remain closed. If it's flat, it will remain flat. If it's open, it will remain open. So the shape of the universe doesn't change over time. The universe has one shape. And our current observations tell us that the universe is mostly flat, but it also might be positively curved as well, which is, I guess, good for the loop quantum gravity perspective. This is actually bad for the holographic perspective because in order for this holographic model of our world, where our 3D space is just encoded on like a 2D boundary, kind of similar to the event horizon of a black hole, except this event horizon will cover our whole universe. This can only be formulated if the universe inside our space is negatively curved, and we actually don't see this. So it's going to be speculative, but a good point, something positive with this is it helps us understand the true nature of these forces, electricity, gravity, how they relate to each other. So it's a good tool for us to explore what these, even though it might not be realistic, it's still a good tool to explore the unification of all the forces. So that's nice. We could get a deeper understanding of what these forces are. So let's see mathematically how to express this curvature. So I wrote this many times now, but this is the expansion in our flat universe. And then it's nice to convert to spherical coordinates. I realize that you might need a little bit of calculus to do this, so let's just ignore that. So instead of doing x, y, z, normally we just do, we could say instead of x, y, z, we do the radius and then the two angles of the sphere. And this is nice to exploit spherical symmetry, like what we would see. So we have a sphere, we have the radius coming this way, and then we have the theta, phi, and pretty much you could just resemble any point in x, y, z in terms of r, theta, and phi. So in this case with spherical, this equation turns into this. So we see that we have this dr squared and then r squared, delta theta, sine theta, and this phi. So this is just dx. Literally same thing. Nothing's changing. I'm just writing it a different way. I'm writing it to make our next calculation easier. Just like how writing it like this made the gravitation, the curvature of the Earth easier to study, since this is the Earth and we just move away from it r. This is the r direction, and then so the gravitation energy changes in this moving away radially, but then it doesn't change as we go along theta, or we move this way in a circle, phi. So it doesn't change, so the only thing that changes is r, so that's why it's better to use these coordinates, because we only have, instead of having like the gravitational field depend on x, y, z, it only depends on one coordinate r, so that's motivation. So this is for flat, so in order to get curvature, we just include this little piece over here, so we divide it by r squared, which is very similar to what we did for the gravitation. We divided dx by some r value. So this is so there you can see why this produces curvature. Unless k equals 0, then this r value disappears, and then it goes back to the flat case. For the closed universe, the positive curvature, k will equal 1, and then for the negative curvature, k equals -1. And then another way to write this that will that you could see the actual shape better. So we said that positive curvature has spherical symmetry, and we could represent a sphere by sines, cosines, and then we could represent a hyperboloid by sinh, cosinh. And yeah, this is like a little confusing. I guess I didn't realize this till after, so I just spelled it out. So it's not like this isn't any fancy notation. I just wrote it in this way, so that there's 3 different metrics you could use. And then if you're doing closed, you just insert this value. If you're doing flat, you just insert this value. If you're doing open, you just insert this value. So that's what I just wrote this out explicitly afterwards. So this is open, flat, closed. So yeah, I mean this is pretty interesting. This was an interesting discussion. I wish I could have got this. I wish I could have done this during the splash class, but oh well, that's nice. I was able to get more done. So enjoy. If you have any questions, please email me. Thank you. And be well.